Now let's go through a quick start for LangChain, showing you how you can get set up with LangChain, LangSmith and LangServe, how you can use the most basic and common components of LangChain such as prompt template, models, and output parsers, how you can use LangChain Expression Language, the protocol that LangChain is built on and which facilitates component chaining. We'll also show you how to build a simple application with LangChain, how you can trace your application with LangSmith, and how you can serve your application with LangServe. Let's discuss the setup. First of all, you'll need to install LangChain. You can do so either with pip or with conda. Afterwards, you'll need to set up the environment. Using LangChain will usually require integrations with one or more model providers, data stores, APIs, and so on. For this particular example, we'll use OpenAI's model API. First, we'll need to install their Python package via pip install OpenAI. Accessing the API requires an API key, which you can get by creating an account. Once we have a key, we'll want to set it as an environment variable by running export OpenAPI key equals, and then you'll have to type your particular API. If you'd prefer not to set an environment variable, you can pass the key indirectly via the OpenAPI key name parameter when initiating the OpenAI LLM class. In Python, we can do this by importing the chat OpenAI class from LangChain chat model, and then we create our LLM variable by instantiating the chat OpenAI object and passing in our OpenAI API key. Next, we'll need to set up LangSmith. Many of the applications you build with LangChain will contain multiple steps with multiple invocations of LLM calls. As these applications get more and more complex, it becomes crucial to be able to inspect what exactly is going on inside your chain or agent. The best way to do this is with LangSmith. Note that LangSmith is not needed, but it is helpful. If you do want to use LangSmith, after you sign up at the link above, make sure to set up your environment variables to start logging traces. Export, for example, you can export the LangChain tracing v2 variable and set it to true, and you can also export the LangChain API key. Finally, we'll also need to set up LangServe. LangServe helps developers deploy LangChain chains as REST API. You do not need to use LangServe to use LangChain, but in this guide, we'll show how you can deploy your app with LangServe. What you'll need to do is to install LangServe using the pip install LangServe all command. After discussing the setup, now we can look at how you can build with LangChain. LangChain provides many modules that can be used to build language model applications. Modules can be used as standalone in simple applications, and they can be composed for more complex use cases. LangChain composition is powered by LangChain Expression Language, or LCEL, which defines a unified runnable interface that many modules implement, making it possible to seamlessly chain components. The simplest and most common chain contains three things: an LLM or a chat model, a prompt template, and an output parser. Regarding the LLM or the chat model, the language model is the core reasoning engine here. In order to work with LangChain, you need to understand the different types of language models and how to work with them. Regarding the prompt template, this provides instructions to the language model. This controls what the language model outputs, so understanding how to construct prompts and different prompting strategies is crucial. Regarding the output parser, these translate the raw response from the language model to a more workable format, making it easy to use the output downstream. In this guide, we'll cover those three components individually and then go over how to combine them. Understanding this concept will set you up well for being able to use and customize LangChain applications. Most LangChain applications allow you to configure the model and or the prompt, so knowing how to take advantage of this will be a big enabler. There are two types of language models: LLMs and chat models. In the case of LLMs, the underlying model takes a string as input and returns a string. In the case of chat models, the underlying model takes a list of messages as input and returns a message. Strings are simple, but what exactly are messages? The base message interface is defined by base message, which has two required attributes: content and role. Content represents the content of the message, usually a string, and role is the entity from which the base message is coming from. LangChain provides several objects to easily distinguish between different roles: human message, which is a base message coming from a human or user; AI message, which is a base message coming from an AI or an assistant; system message, which is a base message coming from the system; and function message or tool message, which is a base message containing the output of a function or a tool call. If none of these roles sound right, there is also a chat message class where you can specify the role manually. LangChain provides a common interface that's shared by both LLMs and chat models. However, it is useful to understand the difference in order to most effectively construct prompt for a given language model. The simplest way to call an LLM or a chat model is using the invoke method, the universal synchronous call method for all LangChain Expression Language objects. LLM.invoke takes in a string and returns a string, while chat model.invoke takes in a list of base message and returns a base message. The input types for these methods are actually more general than this, but for simplicity, here we can assume LLM only take strings and chat models only take lists of messages. Check out, let's see how we can work with these different types of models and these different types of input. First, let's import an LLM and a chat model. We can do this by importing the OpenAI class and the chat OpenAI class and instantiating our LLM and chat underscore model variable. LLM and chat model objects are effectively configuration objects. You can initialize them with parameters like temperature and others and pass them around. Then we import the human message class from LangChain schema. We define a text variable and a messages variable, which is a list containing an instantiated human message object to which we pass our text variable. We can then call the invoke method of the LLM with the text variable provided, and we will get a response. We can also call the invoke method of the chat model and will get back an AI message. Regarding prompt template, most LLM applications do not pass user input directly into an LLM. Usually they will add the user input to a larger piece of text called a prompt template that provides additional context on the specific task at hand. In the previous example, the text we passed the model contained instructions to generate the company name. For our application, it would be great if the user only had to provide the description of a company or product without worrying about giving the model instructions. Prompt templates help with exactly this. They bundle up all the logic for going from user input into a fully formatted prompt. This can start off very simple. For example, a prompt to produce the above string would just be importing the prompt template class from LangChain prompt, setting up the prompt variable by calling the from template method of the prompt template class, and finally calling the format method on the new prompt variable and providing, in this case, the product parameters. However, the advantages of using these over raw string formatting are several. You can partial out variables. For example, you can format only some of the variables at a time. You can compose them together, easily combining different templates into a single prompt. For explanations of these functionalities, prompt templates can also be used to produce a list of messages. In this case, the prompt not only contains information about the content, but also each message, its role, its position in the list, and so on. Here, what happens most often is a chat prompt template is a list of chat message templates. Each chat message template contains instructions for how to format that chat message, its role, and then also its content. Let's take a look at this below. First, we import the chat prompt template class from LangChain prompt chat. Then we initialize our template and human template variable. Then we initialize our chat underscore prompt variable by calling the from messages method of the chat prompt template class, passing in a list with two tuples for the template and the human template. Finally, we call the format messages method of the chat prompt variable with the parameters input language, and the output parsers convert the raw outputs of a language model into a format that can be used downstream. There are a few main types of output parsers, including convert text from LLM into structured information such as JSON, to convert a chat message into just a string, to convert the extra information returned from a call besides the message, like OpenAI function invocation, into a string. In this getting started guide, we will write our own output parser, one that converts a comma-separated list into a list. We import the base output parser class from LangChain schema. Then we define the comma-separated list output parser, providing the base output parser as a base class, and we use this to parse the output of an LLM call to a comma-separated list. We also define the parse method, which takes as parameter self and also a string named text. This will parse the output of an LLM call. We write the logic for parsing the output of the LLM call, and that is our class. Now we can use it by simply instantiating comma-separated list output parser and calling the method parse, to which we can pass a comma-separated string, and will obtain as output a list of strings. In terms of composing with LCEL, we can now combine all of these into one chain. This chain will take input variables, pass those to a prompt template to create the prompt, pass the prompt models to a language model, and then pass the output through an optional output parser. This is a convenient way to bundle up a modular piece of logic. So let's see it in action. From typing, we import the list class. Then we import the chat OpenAI class, the chat prompt template class, and the base output class. We once again have our code that defines the comma-separated list output parser class. Then we define our template and our human template. We define the chat underscore prompt variable by calling the from messages method of the chat prompt template class. Then we define the chain variable as chat underscore prompt vertical bar, then an instance of chat OpenAI, then an instance of comma-separated list output parser. Then we can call the invoke method of the chain variable by passing in a dictionary with the key value pair, text, and colors, and we'll obtain the output as a list of color names. You can note that we are using the vertical bar syntax to join these components together. This vertical bar syntax is powered by the LangChain Expression Language, LCEL, and relies on the universal runnable interface that all of these objects implement. If you've enjoyed this video so far, it will really help me a lot if you subscribe to my channel by clicking the subscribe button and hitting the notification bell. I know most of you are not subscribed already, so you might miss out on any future content that I'll release on this channel. Please subscribe today. Thank you. I recently created a Patreon account for the data science channel. At the moment, I create my videos in my spare time while also working a full-time job. Having a Patreon would allow me to receive donations from people like you who have enjoyed the videos that I've produced so far, and will help me improve the quality and the frequency of the videos that I post on the channel. Moreover, for each of the membership options available, I will provide some extra services for those of you who decide to support me. Essentially, you can pick between 3 tiers of membership. In the associate tier, you can provide me with the equivalent of a cup of coffee. I would provide you with all the materials and the code that I use during my videos, and with a monthly live session with myself where you can ask questions and we can discuss various topics related to data science. If you want to support me even further, you have the senior data scientist tier, where I'll also provide you with monthly one-on-one sessions with myself, where I'm going to provide you with guidance, mentorship, and answer any questions regarding your data science journey. Finally, for those of you who are more generous, you can opt for the lead data scientist tier, where I'll be happy to provide weekly one-on-one mentorship sessions, and as a bonus, I'll produce a 1-hour-long tutorial about the data science topic of your choice once you've been a member for 12 consecutive months of the lead membership. Each higher membership will contain all the benefits of the previous membership tier. So for senior data scientists, you'll also get the the benefits of an associate data scientist, and for a lead data scientist, you'll also get the benefits of an associate and senior data scientist. I would definitely recommend you to consider supporting me in this journey. Regarding tracing with LangSmith, assuming we've set our environment variable as shown in the beginning, all of the model chain calls we've been making will have been automatically logged to LangSmith. Once there, we can use LangSmith to debug and annotate our application traces, then turn them into dataset for evaluating future iterations of the application. Regarding serving with LangServe, now that we've built an application, we need to service it. LangServe helps developers deploy LCEL-Chain's API as a REST API. The library is integrated with Fast API and uses Pydantic for data value. To create a server for our application, we'll make a serve.py file with three things: the definition of our chain, our Fast API app, and a definition of a route from which to serve the chain, which is done with LangServe add route. We first import the list class, the Fast API class from Fast API, the chat prompt template, chat OpenAI, base out parser from LangChain, and the add route method from LangServe. Then we move on to the chain definition. We define our comma separated list output parser class, then we define our template variable, our human template variable, our chat underscore prompt variable, which we obtain by calling the from messages method on the chat prompt template class. Then we define our category underscore chain variable as chat prompt vertical bar, chat OpenAI instance vertical bar, comma separated list output parser. Then we write our app definition and we use the Fast API class to instantiate our app object. And finally, we add the chain route by using the add route method, to which we pass our app, our category chain, and the path, in this case category underscore chain. And that's it. We can simply execute the file using Python serve.py, and then we should see our chain being served at localhost 8000. Every LangChain service comes with a simple built-in UI for configuring and invoking the application with streaming output and visibility into intermediate tests. Head to localhost 8000 category chain playground to try it out. To set up a client for programmatically interacting with our service, we can easily do this with the LangServe.remoteRunnable class. Using this, we can interact with the serve chain as if it were running client-side. First, we import the remote-runnable class from LangServe. We instantiate the remote-runnable. We assign to the remote chain variable an instance of the remote-runnable class. We call the invoke method on the remote underscore chain variable, passing a key-value pair composed of tag and colors, and we received as output a list of colors: red, blue, green, yellow, and orange. In terms of security, LangChain has a large ecosystem of integrations with various external resources like local and remote file systems, APIs, and databases. These integrations allow developers to create versatile applications that combine the power of LLMs with the ability to access, interact with, and manipulate external resources. In terms of best practices, when building such applications, developers should remember to follow good security practices, such as limiting permissions, anticipating potential misuse, and defense in depth. In terms of limiting permissions, scope permissions specifically to the application's needs. Granting broad or excessive permissions can introduce significant security vulnerability. To avoid such vulnerabilities, consider using read-only credentials, disallowing access-sensitive resources, using sandboxing techniques such as running inside a container as appropriate for your application. In terms of anticipating potential misuse, always assume that any system access or credentials may be used in any way allowed by the permissions they are assigned. For example, if a pair of database credentials allows deleting data, it's safest to assume that any LLM able to use those credentials may in fact delete data. In terms of defense in depth, no security technique is perfect. Fine-tuning and good chain design can reduce but not eliminate the odds that a large language model may make a mistake. It's best to combine multiple layered security approaches rather than relying on a single layer of defense to ensure security. For example, use both read-only permissions and sandboxing to ensure that LLMs are only able to access data that is explicitly meant for them to use. Risks of not doing so include but are not limited to data corruption or loss, unauthorized access to confidential information, compromised performance, or availability critical resource. Example scenarios with mitigation strategies: a user may ask an agent with access to the file system to delete files that should not be deleted, or read the content of files that contain sensitive information. Limit the agent to only use a specific directory and only allow it to read or write files that are safe to read or write. Consider further sandboxing the agent by running it in a container. A user may ask an agent with write permissions to an external API to write malicious data to the API or delete data from the API. To mitigate, give the agent read-only API key or limit it to only use endpoints that are already resistant to such misuse. A user may ask an agent with access to a database to drop a table or mutate the schema. To mitigate, scope the credentials to only the tables that the agent needs to access and consider issuing read-only credentials. If you're building applications that access external resources like file systems, APIs, or databases, consider speaking with your company's security team to determine how to best design and secure your application.